The all-new motion planning module completely redesigned the detection and planning algorithms from the ground up, revamped the configuration interaction for picking and retract paths, supports adding multiple pre-pick and pre-retract points, added a new planning details panel, displays detailed detection results for each path. At the same time, significant optimizations have been made to the visualization of robot motion trajectories and collision detection areas in the view, making it easier to understand, configure, and debug, and greatly improving the efficiency of building project solutions. Next is a simple case study of picking T-shaped pipes to introduce our new motion planning module. First, add a tool. Click the plus button on the right side of the tool. We can upload a tool model in OBJ format. However, the tool model uploaded here is not a regular OBJ model, but a convex hull model. For any straight line passing through a two-dimensional shape, if the line intersects the shape only twice, then the shape is considered convex. Conversely, if a line can be drawn through the shape that intersects it more than twice, then the shape is non-convex. Similarly, for a three-dimensional polyhedron, if any line passing through it intersects its boundary only twice, then the polyhedron is a convex polyhedron, referred to as a convex hull. When a complex three-dimensional model is entirely composed of convex hulls, the model is called a convex combination. Once the scene configuration is set up, and camera parameters and algorithm parameters are configured, the next step is the motion planning configuration. First, we need to set up the collision detection pairs. Note that two parameter items are introduced here, which will affect all collision detection pairs configured subsequently. The first is the collision grid edge length. Simply put, we will convert the point cloud involved in collisions into small cubes. This parameter is used to set the edge length of these cubes. The smaller the edge length, the more cubes there will be, and the more precise the collision detection will be. However, the corresponding computation time will also increase. The second is the detection mode. Fast mode. During the planning of a robot path, if any collision point pair of a path point collides, the collision point pair detection and the remaining path point collision detection are immediately terminated. Full mode. During the planning of a robot path, regardless of whether any collision point pair of a path point collides, all collision point pairs preset in all path points of the path are fully traversed and detected. Click any small block in the matrix to configure the collision threshold for that detection pair. The software will automatically determine the detection method for the collision threshold. For collision detection involving point cloud models, select volume. You can set any value greater than or equal to 0. If both detection objects are OBJ models, then distance will be used, and the threshold is fixed at 0, which can't be changed. Before configuring path planning, first, you need to determine the return position type. According to the communication program of the robot, select Cartesian here. The next step is path planning. In order to better understand and debug, we divide the entire plan path into 4 sections. The first section refers to the start point to the pre-pick point. The second section refers to the pre-pick point to the pick point. The third section refers to the pick point to the pre-retract point. The fourth section refers to the pre-retract point to the end point. For the pick path, the following parameters need to be set. Number of waypoints. For the pick path, this includes the waypoints from the initial planning point to the pre-pick point, as well as the final pick point. This path at least includes the start point, pre-pick point, and pick point. Therefore, the minimum value is 3. The more waypoints there are, the more waypoints there will be between the initial planning point and the pre-pick point, resulting in higher path reliability, but the corresponding planning time will also be longer. The final value should be determined based on actual project requirements. Here, we will use the default value of 20. Joint angle difference threshold is used to set the maximum allowed angle range for a single joint between two adjacent path points. During actual planning, if the threshold is exceeded, it will report that the waypoint is unreachable. Here, we'll use the default value of 180 degrees. There are three types of motion planners: joint space planner, linear planner, and Bezier curve planner. The joint space planner plans based on the angles or positions of the robot's joints. It directly calculates the path each joint needs to rotate or move, from the start point to the end point, typically generating a smooth joint angle curve. The path is not a straight line in space, but a smooth change in joint angles. The linear planner is based on the Cartesian coordinate system, that is, planning with x, y, z coordinates in space. Linear planning. It ensures the robot's end tool moves along a straight line in space, from the start point to the end point. The Bezier curve planner is based on the mathematical Bezier curve to generate a smooth curve trajectory. The Bezier planner has two adjustable parameters: the curvature at the start point and the curvature at the target point. Simply put, the smaller the curvature, the straighter the curve resembles a line. The larger the curvature, the more curved the curve becomes, resembling an arc. Set the start point. The start point serves as the beginning of motion planning, to ensure the planning algorithm can start planning the path from a known state. The current version still requires the robot to set the waypoint to prevent situations where manually input waypoints are unreachable by the robot. After moving it to the target position, simply update the plan point's pose. Setup complete. Click the setting button on the right side of the waypoint to further modify its related attributes. Add pre-pick point. The pre-pick point is usually located near the target object, serving as a transitional position for the robot before the actual picking, ensuring the robot can complete the picking task with a suitable posture. To reduce computational complexity, a linear planner is used from the pre-pick point to the pick point. It means the TCP maintains its posture at the pre-pick point and moves in a straight path to the pick point. Therefore, the pre-pick point is typically set by defining an offset relative to the pick point. Of course, you can also choose to offset along the robot coordinate axis, or customize the direction according to actual situation. Set an appropriate offset distance and detection step length. The offset distance and detection step length are used to define the collision detection interval on the straight path from the pre-pick point to the pick point. This means that along the straight distance from the pre-pick point to the pick point, collision detection is performed at regular intervals to ensure safety. Similarly, we support adding multiple start points and pre-pick points. Of course, multiple pre-retract points and retract endpoints can also be added. When a collision occurs at the first pre-pick point, it will switch and use the next alternative pre-pick point for planning. For a single pick point, the more waypoints are added. For a single pick point, if there are no exceptions, then start planning the path from pre-pick point 1 to the pick point. If there is an inverse kinematics failure or a collision exception occurs, then switch to the second start point to replan the path, and so on to test one by one. Including the retract path planning is similar. It can be foreseen. If multiple waypoints are set, the calculation results of path planning will be very complex. The software provides a planning details panel, which can print all results layer by layer, according to the above-mentioned approach, specifically corresponding to. The first layer is the pick point, the second layer is the path, the third layer is the different segments split from the path. If there is only a pick path, then there are two segments. If it includes a retract path, then there are 4 segments. To most intuitively indicate which segment of the path it is, the name of each segment is formed by concatenating the start and end path points. The fourth layer is the collision detection details of the path points. It will print the detection pair calculation results for each path point location. Pick point details. Click to view the name of the pick point, index, priority, pose, ID, and other information. Display path. Clicking will draw this path in the view. These waypoints can also be clicked. You can also find this path in the panel. Click the positioning button after the waypoint. You can also achieve the effect of robot movement. Click again. The robot will return to the initial position. Up to this point, what is seen in the panel is all green non-abnormal states, indicating no collisions occurred on the path. In addition, there are several other abnormal states, each marked with yellow, red, or grey. Yellow indicates a collision has occurred. Specific collision details can be viewed in the panel. If it's a collision between convex hulls or convex combinations, it will display a yellow D equals 0. If it's a collision with a point cloud, it will show the specific number of points in the collision volume V in yellow. Red indicates an unreachable pose, usually due to two reasons: failure in the robot's joint inverse solution, or joint angle differences exceeding the threshold. In the planned path, if even one waypoint pose is unreachable, the robot will not proceed along that path. The remaining waypoints will no longer undergo collision detection, and naturally, there will be no collision information. These waypoints will be marked in grey. Now, let's run it in practice. See how to use the Planning Details panel to assist in debugging. The robot starts picking from the second workpiece. The first workpiece is marked in yellow, indicating an abnormal situation. Open the Planning Details panel. Let's take a look at the specific information. Pick pointer labeled as 0 is marked in yellow, indicating a collision occurred. Click to expand and check the cause. It can be seen that the algorithm tried 3 different paths, but all reported collisions and failed to pick. The issues all lie in the retract path. Continue clicking to expand. The failure of the first path is due to an issue at path point 5. The note in parentheses explains that a collision occurred at the pre-retract point 1 position. To make it clearer, click to display this segment of the path, then move the robot to the accident position, and play it back for observation. Continue clicking to expand. Details show that it's due to a collision between the no 0 picking object and the scene point cloud. The collision volume is 173. Click on this collision pair. The view will display red collision meshes, indicating the actual positions where the collision occurred. It's clearly visible that this is caused by an unreasonable pre-retract point position. When the robot returns after picking the workpiece, it collides with other workpieces, resulting in planning failure. So click on the Settings panel for pre-retract point 1. Change its offset direction from along the positive Y direction of the picking point to along the negative Z direction of the pick point. Then retest the effect. After modification, successful picking is achieved. Continue clicking to plan and see if the bin clearing can be completed. The last workpiece is highlighted in yellow, planning failed. Still, proceed to open the Planning Details panel to troubleshoot. Tried 4 paths. All reported failures. Among them, Path 1 experienced a collision between pre-retract point 1 and end point 1. Upon further expansion, it can be seen collisions occurred at waypoints 2, 3, and 4 respectively, but everything is normal after waypoint 5. Additionally, because the collision information shows it's a collision between the picked object and the bin, so it can be concluded that during the retraction process, the robot carrying the workpiece scraped against the bin. Try changing the offset direction of the pre-retract point to move it away from the bin wall, then attempt the planning again. Planning successfully completed the bin clearing and picking.